Okay, so where we left off yesterday, we did the example, but the explanation of the event loop was given hurriedly. So I am explaining it once more. So that was a file um, which we have to open. Yesterday we were working in root stuff 1. So root stuff 1, which was unpacked from here, is now here. So I'm opening root stuff 1 again, and the macro which does this event loop was in the second. The first macro was easy, the second macro was more involved. So I'm going to open this macro and then show you the relevant lines for the event loop and how it works. So if I double click this file, then it opens in the editor, and in the editor I'm explaining the parts. So in any macro, it always starts by putting it as a function, and the name of the function should be the same as the name of the macro. And usually macros don't take arguments, so we are not supposed to put anything inside the bracket here. Now you will come more about macros just after this. I'll go into a detailed explanation about macros and with many examples. Right now I am concentrating on explaining the event loop. Once again you will see more examples of the event loop, and I will also show you a second way of doing this event loop. So you have to understand both the ways, and both are good. You can use whichever one suits you. So in the beginning, these definitions of these are the part which I have highlighted are the definition of the histograms. These commands have been explained earlier. You have to type them correctly. And this first line here, this one opens the tree. So there is a file which contains the data, and that is this teles100.root. First duty is to open that file, and then you have to get hold of the tree which is inside this file. So as explained, all the files I am giving were generated from LAMMPS itself, so that's why the tree name is LAMMPS tree. But when you have other files, the tree name would be different. So you open the tree with this command, and then you define the histograms which you are going to build. So this macro, what it does is it tries to build the histogram. So this is the most important macro which you need to preserve with you. It's a sort of an example template for almost all your work, because your work consists of opening a root file and building histograms. So how do you do that? So this is explained in this, and we'll see one or two more examples soon. So the procedure for doing that, and then to get arbitrary sizes of the histogram. By arbitrary I mean your decision at what size you want the histograms, not leaving it to root to decide, but you deciding what is the size of each histogram. This is provided only through this. So this example is very important to understand. It starts to make the loop. First we need to know the loop will go up to how much. So this command which I have highlighted calculates the quantity called n entries. I have given it a name, n entries, you can call it anything. It actually finds out the number of entries in the tree, which another way of saying it is, if it was an Excel sheet, a CSV file, then the number of lines in it. So basically it is a number of events. In a CSV file, every line is an event, every column is a parameter. So I'm in root, the terminology is different. We don't consider it as an Excel file, and we don't talk about lines inside the Excel file. Instead, we talk of how many entries it has got, and the entries is to be calculated, is to be obtained first into our program, so that when we make the loop over events is here, which I am highlighting now. So to make this loop, we need to know the loop must start from 0 and it should go up to the last entry. And to know how many entries are there, we execute first this command. So just for our information, which later on you don't need to do it, but I have displayed how many entries we have by printing it out explicitly. So if you don't want to print it out, it's okay. The main thing is that the value is available inside the program. Now comes the most important part. For each of the leaves in your data, so in this kind of data doesn't really have branches. There is a tree, and what you have are really leaves. So here we don't have to distinguish between branches and leaves. So this command, my tree or any other tree which you have, so my tree was actually defined here, and my tree is nothing but the lamps tree which we have attached to this variable my tree. So we make my tree execute a set branch address. So what this set branch address does is that here in the first argument you have to give the name of the variable, and the name of the variable must match with whatever the name of the variable was inside the root file. So this is the root file, and you have already explored this root file by the other methods which I have mentioned. Before you start writing the program, you must already be aware not only of the name of the root file but also the name of the tree, and you must be aware of all the branches. So we already know the name of the branches. The name of the branches in this file are delta E, which we call DE, and E dash, which is E residual. So these names must correspond. If you make a mistake here, then it won't work. We need to have the name of the branch correct, and that name of the branch I had shown you earlier with the help of the print command how to get it. So you can always find out before you write this macro that what are the names of the branches. So having supplied here the names of the branches, next comes the variable into which you want to place that data. So the data is presently in branches, and it has to come out of the branch and it has to enter into your program. That means this macro. This macro is a program which will be running, and this macro needs access to the values of the leaves. So what we have done is, before we execute these tree set branch address commands, we first define the variables here. So there are two variables I am using. The first is delta E, I call it as DE, and then is the E dash, but E dash is you cannot use, it's not a valid C++ variable name. So I call it ER, that means E residual, and I put it here. So what these two commands do is it maps the tree quantities delta E and E dash, it maps them into variables inside your program. And for those of you who know C or C++ will realize that this AND character here, it is called as the address of operator. Its significance is that we want this root program, which is setting the branch address, to have access to the memory location where delta E is sitting and where ER is sitting, so that he can put the values, insert the values at those locations. So here we cannot put only delta E or only ER. We must put the AND sign in front of it. The AND sign signifies the memory location. It changes the value into a pointer. So the value is DE, the value is ER, but a pointer to DE is the address of that. So AND DE refers to the pointer where DE is sitting, and address of ER is a pointer to ER. So root needs the pointers to these two variables. Why two variables? Because that's what we have. In this tree there are only two variables. In a more elaborate program you will have many variables. All of them have to be set up in this same way. So our examples are kept small, and real life examples will have more parameters, but process is the same. Now we begin the loop. So after you have set up the branch addresses, then you have to begin the loop. It's only this much. So what we do is we start a loop. The loop starts here. The loop index is I, and I must run from the first event to the last event. So it goes from 0 and less than n entries. I will be incremented by 1. So this is your loop, standard C loop. And the first command inside the loop has to be this always. So it gets the entry number I, means it's reading one line from the CSV file. This is what you can say. That means it's reading the first entry. As soon as it reads this first entry, my tree, as soon as this line is executed, these quantities delta E, that is DE and ER, will get values. Before this line is executed, there was no value sitting there. There was no number. But so by default it would have been 0 sitting there, or some random quantity sitting there. There was no number sitting inside inside these variables. But as soon as you execute this command, then both DE and ER will have values inside it. So ER and DE both have got values after this command is executed. Once they have values, then you can also manipulate these values. So in this example, we have done calculation of E total as E residual plus 0.34 delta E, which is similar to, which is the same as what we had done earlier on this same file when we were analyzing it in LAMMPS. So you can refer back to the PowerPoint which was presented on that day, and you will understand why this number 0.34 has been put. And also in that lecture, the particle identifier was explained, and this was the definition of the particle identifier. So it was the E total raised to the power of 1.7 minus the E residual raised to the power of 1.7. So this POW is the power function in C++. So we use POW, it means raising something to the power. So these two quantities are what are called as pseudo variables in LAMMPS. Here we don't need a nomenclature like pseudo variables. Whatever we want to do, we can do anything at this point. Once we are inside the loop, we have access to the two quantities which are root variables, that is the first two this. And here I am creating two more, but it's up to me, whatever I want I can create. And so arbitrary mathematical operations can be done inside this event loop, and the original two parameters which were in the file, from them we can derive new quantities without any problems. Just by writing lines in the program, we can do whatever we want. After that, you have to fill the histograms. These commands are known to you from our earlier experiences. So we have defined 5 histograms. I think 1, 2, 3, 5 histograms are defined. 2 one-dimensional and 3 two-dimensional histograms are defined here, and we fill them. So the first one we fill is just a one-dimensional histogram of delta E. The second one is a one-dimensional histogram of ER. And the third one is a two-dimensional histogram of ER versus delta E. So they are based on the raw data. But in addition, we have created this another histogram where ET is the total energy which was not available in the root file. We derived it over here by mathematical calculation, and we put that along the x-axis and we put delta E along the y-axis. And for the last histogram, we fill it with the total energy along the x-axis and the particle identifier along the y-axis. So we have run this example already yesterday. I run it once more just to finish this part, and now you have gained an understanding of what event loop is, and hopefully you can write your own event loop. So you have to keep this file with you for any further work you do in root, and start with this file and then modify it according to the actual data which you are having in your experiment. So that is how to remember all these commands is difficult. So even for me, all these files are there in my records, and I open these files and have a look, and then I work further on any other problem. So these basic files should always be with you. Any person who works in root should have a set of files with him, and he uses those files and does cut and paste from there to actually create the bigger file which he needs for the actual data. So I'm going to just run it, but of course I ran it already yesterday, so this is just for completeness. So to run it, we go to the directory, and this is the macro which we are going to run. So we right click here and then say open in terminal. Now the terminal is opened, but in the correct directory. So from here we are going to run root, and there are three ways of running a macro. One of the ways of running a macro is simply to mention it here itself. So if we do it like this, then in one command, root will start, it will load and actually execute this macro all in one go. So if I do that, then it says here that he was able to process it, and this is the thing which we were only printing as part of our program. We had asked printing out of the number of events, that is the number of lines in the CSV file, and it is 2 million. And here are the graphs which were generated. So these are the spectra. So I generated them on 4 different canvases. I combined the first 2 spectra on one canvas, and then I made this on the second canvas, and then I made it on the third canvas, and this was the one on the fourth canvas. So this completes my first explanation of the event loop, and now we are going to see some more macro examples, and we are also going to see another way of writing event loop which is similar, slightly different. So you will know both the ways how the event loop can be constructed. So right now we are going to do some simple examples, simpler than this. Consider this as more complicated, and to understand root macros, we are going to do something first easier and then build up slowly. So now I'm going to quit root. One of the commands is you can put here .q, this will end root, and still another method is from any of the canvas windows which are open, you can do the last option, which is quit root. So I am doing now this one which we have not done before, so this method is also good. And you will notice that we are back on the Linux command line. Root is gone. Now I want you to download and create another folder, then that will be called as root stuff 2. It's also on the website. So if we go to the website now, I will show you root stuff 2. What we did was up to now was root stuff 1. So in root stuff 2, in the lectures tab, I have put now this one which was not there earlier. So you have to click this and download it into your downloads folder, and as usual then you have to copy it into the main your home directory. So that means after you download it, if you look into your downloads folder, it would have reached here. So this is the file which I have downloaded, and it has reached here. Now I must copy it. So I did Control C, or you can do right click and copy, and then you go to your home directory and then you paste it here. So I pasted it, it gave rise to root stuff 2, and now I am going to extract here. I do this command extract here, and when I do that, then another directory opens, and that is root stuff 2, and then I go to that directory. So this is my new directory, and these are the files. This I am going to explain. Here I have created 1, 2, 3, 4 macro files, and later on I will show you how to write complete programs. So there are 4 complete programs also. So 4 macros and 4 complete programs, and this is the file that we are going to use. Cobalt60.root. This is going to be the root file which we are going to analyze. So first I explain what is this Cobalt60 data. So I will open this PowerPoint presentation for you. So this is a very basic MSc lab experiment. We did this. I was, by the way, a student of Delhi University. So those of you attending the course who are from Delhi University will be happy to note that I am also from Delhi University. And even that time when we were studying, this experiment was included in the MSc practical class. So what we did there, well, I'm just modernizing it so that you have list mode data. We could not have done list mode data and root analysis in those days. And maybe in a lab, a small MSc lab facilities may not exist for taking the list mode data, but basic experiment was done even in those days. So what was done is that there are two sodium iodide detectors. I call them NaI1 and NaI2. So there are two sodium iodide detectors. There is a cobalt 60 source which is placed in between the two detectors, and then the output, so from the back of the sodium iodide detectors you have this photomultiplier tube bases, and all the photomultiplier tubes always have two outputs. One is called as the analog output or the amplified output, and the second one is the timing output. So here I am putting then the output from, actually this should really be QDC rather than ADC. As far as you are concerned, it won't matter, but this should really have been a QDC on which we take the output from a photomultiplier tube directly if you want to put. So this should have been, there are two QDCs here where I call those signals G1 and G2. And regarding the timing signals, we send them. So I want to generate a trigger from the first sodium iodide. So what I do is I put a discriminator there, and the discriminator output I use it for triggering my acquisition system. At the same time, I want the time between the two. So this one should start and this one should stop. So I keep a TDC here, and I start it with the help of T1 and I stop it with the help of T2. I introduce a delay in the T2 branch to make sure the stop comes after the start. And this is the circuit. So we use this exact same circuit in MSc lab, except that we didn't have a acquisition system, but otherwise it was done by using scalar counting. But now you can do it in a more modern way like this. So then you have basically parameter 1 will be the energy of the first gamma ray, parameter 2 will be the energy of the second gamma ray, and parameter 3 will be the time between these two pulses. So it got started with this and got stopped with this. A time difference between T1 and T2 that will be digitized, and that will come in T. So this is the data. Have then collected it. I have also collected this data in a virtual way. So this is not real data which I am going to show. It is again idealized data. And this data I will be showing the cobalt spectra, but without Compton effects, only the photo peaks, just to simplify. So that's because this is not real data. In real data, the Compton scattering will be very high, but here this is not real data. It's simulated. So I have avoided the Compton part in the simulation so as to make it easier for us to understand. So let's go to the data. And as usual, when you meet a root file for the first time, how do you start to analyze it? Is that let's open a terminal, and then in this terminal we will start root. So root has been started, and if we want to explore what is the tree sitting inside it and the name of the parameters, this should be our first task, and this you have done in the past, so all of you know how to do that. First you have to put the file name and open it. So that command is like this: tf is equal to new t file and then you give the name of the file. In this case it is 60 cobalt dot root. I just pressed the tab character, so there were other choices, so it didn't catch it fully. It will catch it now if I press tab. So yeah, so this is the T file which I want to open, cobalt 60 dot root. And if I take a listing of it by .ls, then I find that the tree it contains is called as lamps tree, because this file also was generated by converting it from CSV by using the lamps program, and lamps likes to name the trees like this way, so that's why this name came. In your actual data, the tree name would be different. So having learnt about the tree name, the next is to know the parameter names, so which we have to print it out by giving the command lamps tree and then print. When I do this exercise, then I come to know the names. So the names are G1, G2 and T, as explained already to you in the PowerPoint. All the three of them are type short. That means that is indicated here. So when I get these variables, I will assign them to unsigned short variables. So that completes the initial probe of the data. Now we must actually proceed with our macro, which will read this data, and we'll go ahead to analyze the data. I will now go step by step. So I will demonstrate to you how to write a macro, how to save it, then how to execute it, starting from very simple macros. So I am going to start by the first macro one, which actually doesn't do anything, but it is a valid macro and it will be able to explain to you what a macro is. If I start very simple, it's always better. So I am going to start with macro 1. So what I have in macro 1 is nothing at all except a welcome message. So the structure of a macro always, as I explained, first you have to say void and then you have to give the name. This name should be the same as the file. The file name should be macro1 is the name here, and it should end in dot capital C. And having got that name macro1, this name here of the function should match with that. So this should also be macro1. And after that there should be a curly bracket opening, and at the end there should be a curly bracket closing, and in between you can write the macro. I have not written anything in the macro beyond a welcome message. Now those of you who know C programming will agree that this is a valid C program function, C function, not a complete program. But it has one problem, and that is that IOStream has not been included. So if you were to have normal C program, if you were writing this and trying to execute it, it would have given an error on this line because Cout is undeclared. It is actually in IOStream header file, and it has to be also a namespace for std has to be declared in order to use this. But here this is a macro. In a macro we don't need headers and we don't need the namespaces. So in macros the root will run this macro and he knows all about headers and he knows all about namespaces, so we don't have to put it. And in fact in root there is IOStream which he has called as a root IOStream.h, r-iostream.h, which is similar to your normal IOStream. So he has made a new one and the name of it is root, it is r-iostream.h, but here, as I said, we don't have to include it here. So we don't include anything, and the macro is ready. So if you now want to run this macro by saying dot execute dot x is execute and then macro1, and you must put the name of the file. You cannot say now dot execute macro1, that would be wrong. It has to have the full file name, and that means it has to be macro1.c. When I now let this line go through, you will see that this is what it did. It didn't do anything because there was nothing in the file. It just has a message, welcome students, and That's what it did here, printed it out. So this is the first macro that we ran. There was nothing much that we did, but you understood what we did. So we are going to go to the second macro. Now we go to the second macro. So now we are in the second macro. I take away the first macro. So this is my second macro. Now you know the rules for the macro. This is called macro2 dot capital C. So the function name must be void macro2 with nothing inside the bracket. Then the curly bracket should start, and at the end of the program the curly bracket should close, and in between we can put what we want to do. So here I am giving an example. This kind of example I have done already for you manually from the root command prompt, where we declare a histogram. So this is a histogram declared like this, and then we fill it with a few manually defined commands like this, and then we create a canvas. I call it C1, and finally I draw on that canvas this histogram. And then I also try a second histogram, which is a two-dimensional histogram. I fill it with some filling commands like this, and then I make another canvas, and then I draw on that canvas. So this example manually you have already done. That is from the root command prompt. Now we just put all those commands inside a macro, and we try it out. So here I am going to execute the second macro. So macro2.c is going to get loaded and executed, and when I do that, the graphical window will appear here. So I am going to just move these away from here so that it doesn't obstruct. So here it goes. So as promised, it opened two canvases, C1 and C2, and it placed inside it the histograms which we had manually set the bin contents. And this example you have already seen previously in the, I think in the early lecture on root, where we were setting up the histograms and entering the contents manually. Okay, now let's go to the third example. The third example will be macro 3. So I am going to close these canvases, and let us open third macro now. Now this is my third macro, and again, so what do we have? So now I am introducing event loop. So first two examples are done. This is my third example of macro. Now you know the rules for the macro. So first line should be like this, and it must have the curly bracket begin and curly bracket end. And now I am going to do an event loop. I am going to open this file, C cobalt60.root. So this will be opened by this command. So as I mentioned, inside macro, you can't just write this TF has to be defined. So I have defined it here. Another way of defining it could have been here itself. You could have said here T file. You could have written like this also. This would have been equally valid, and then you would not have required this line. So you could have done it like this also. So both the methods I want to illustrate. So I have done it by first defining what is T file and TF as a T file, and then I have used it to open this cobalt60.root. Then I need access to the tree. The name of the tree is lamps tree. So this tree command does it for me. Tree must be defined. Tree is a variable. As before, I can also put the definition, this part I can put it here before this line. It's possible for me to put it the definition in this line itself, but here it has been done separately. So both the methods are valid. Then this you have seen before. I need the number of entries. Here I have already declared this variable and entries, so I am not declaring it again over here. And this command then will get me the entries, and like before I am printing out how many entries are there. So this print will print out the number of entries. Then, as in the previous telescope program, we have to have a loop. Here I am not doing any derived quantities, just the three variables g1, g2, t. But instead of, so like before, I have to first define them here. So they are here, in their g1, g2 and t. I have them here. But instead of using that get branch address and then putting the address operator, there is also another way which might be easier for you to understand if you are not familiar with pointers and addresses. So here is another way. So I can get the tree, and then from the tree I can get the leaf. The name of the leaf is G1, and then I can get its value. That will be a number, and that number I can assign it to my variable G1. So I have defined what is G1 is here, and this part will get from the tree that value, and it will place it inside my G1. So this way also is okay. Here I am doing it by fetching the value from the tree and then placing it myself. In the previous other way of doing it, the address of the variables was given, and root was directly placing it inside that address because of the previous set branch address commands. So this is a manual way of doing the same thing. So you can choose whichever way you like. So this is another way. So here there are three variables totally, and all of them have been done by this method. Now having got it, next job is to fill up. So I am going to fill this one dimensional histogram with G1, I am going to fill the second histogram with G2, and I am going to fill the third histogram with T, and I have made another histogram which is two dimensional, G1 versus G2. And then I define 4 canvases, and on each canvas I draw one spectrum. So H1, H2, H3. So there will be 4 canvases, and so this is my complete macro. So let's execute this now. So I am executing macro 3, and now two things to be noted before I show you. You can watch what happened here. First came n entries. So this file has also got number of events which is 1 million. But he says warning in this that there is already a canvas C1, because we ran the previous example macro 3 that had already created C1. Now this fellow, this new macro is also trying to create. So he destroys the previous C1, and in its place he brings in the new C1. Now this would not have happened if you had started from the beginning. So ideally, before you ran this macro 3, you should actually have quit, and you should have started macro 3 only. You should not have anything to do with the previous macros. So that's why this came. So if you were to do it from here directly, then it would not have complained like this. So here I am doing directly without having the previous macro. See, now there is no complaint from his side. He has created 4 spectra. I'm trying to move them so that you can see them. So this is my first spectrum. It is gamma 1 spectrum. It's a cobalt 60 source. I have avoided the Compton background. So what you have are 2 peaks. They are the 1173 and the 1331, the 2 energies of cobalt 60. Then this has happened in my first detector, sodium iodide 1, and then comes my second detector, gamma 2, which is in the second detector. Now notice how it is interesting that there are 2 peaks here. You can barely see them. They look very small. And so why is it so? So I will just enlarge this. So if I zoom it here, now you will be able to see that they were not so small after all. But it's only that the plot was not able to, because the plot is auto scaling, and there is a noise in this detector. In this detector, there is a discriminator put. You remember from the PowerPoint which I showed that we took the trigger from the first detector only, and there was a discriminator in that. So that discriminator cut off the noise in the detector. But in this detector, the noise cannot be cut because the its discriminator output is not put in the gate, is not put in the trigger. So when I display this in full scale, unzoom, then this is the result, that there is a noise on this left side. I will zoom it so that you can see it. See, this is my noise. This is typical in all experiments. You will get noise in the low channels. So low channels have noise, and then you get the spectrum afterwards. I am going to unzoom it back again. So this is the full spectrum. The real peaks are sitting here, and all this left side is noise. And because this is auto scale, so he tried to make the scale very large so as to display this huge noise. But when you do this example in LAMMPS, which I am also going to do today now, you will see that LAMMPS is aware of all these problems, and he does not auto scale the noise portion on his own. LAMMPS will show this again a little bit bigger. So you see, this is the noise, and these are the two peaks. And since root is not necessarily meant only for this data, it is a general program, so he cannot do anything special. He leaves it to you to understand your data. But LAMMPS knows that you are doing nuclear physics work, and all nuclear physics work have this problem of noise in the low channels. So LAMMPS knows that this part will confuse you, and he will automatically on his own he will avoid the noise scaling, and you will see a graph similar to this directly when we do LAMMPS. So there are many features in LAMMPS which are automated. Don't expect that to happen in root. So those who run root for the first time, they get worried. So when they see this one, they wonder what is happening. But if you just think about it, then you realize that there is not really any problem. It is that way only. So I am trying to unzoom it back again. So I have to press unzoom. Okay, so that was that. So now you understood about zooming consideration. Now look at this one. This is the timing spectrum. At first sight it looks empty, so you may start worrying that what has happened, I didn't get any data. So again, LAMMPS knows about these problems, and he would have, the data is actually lying here, he would have already taken care of the scaling of the spectrum. So this is also heavily scaled. I undo it for you so that you can again see the original one. So this is heavily scaled. Look at the y-axis. It is 800 multiplied by 10 raised to 3. And all that data is sitting in the last channel, because you got the start and the stop never came. Those kind of conditions. So, the coincidence rate is low. The actual data rate is high. We have taken the trigger from the first detector. We didn't make a coincidence between 1 and 2. If you had made a coincidence between 1 and 2, then this last channel data, which is coming at the last channel 4096, this would not have been there. But since this one has got heavy data in the last channel, he has scaled it according to that. And you fail to see the important part until and unless you zoom it, avoiding the last channel. Then you begin to see. And lastly, there is this G1, G2 gamma ray spectrum, in which you see the you see the spectrum. Then there are two cobalt 60 peaks along both axes, so that's why you give a total of 4. So the one, this peak for example represents gamma 1 in both the detectors. So gamma 1 has come in one detector, and gamma 1 has come in the other detector also. And this one is gamma 1 versus gamma 2. Sorry, this is gamma 1 in first detector, gamma 2 in second. And this is gamma 2 in first and gamma 1 in second. And these two are the random coincidences of gamma 1 versus gamma 1 and gamma 2 versus gamma 2 itself. They are less in number. So this comes from random coincidence, and these come from the true coincidence, these two patches. And these two patches have come from the random coincidence. Their count rate is lower. But additionally, so I am unzooming by using the scroll wheel of the mouse. See this. So these are the again randoms where one detector has given data, the second detector has not given the data, and the trigger was taken from the first detector. So first detector has data, but the second detector has no data, and that gives rise to this. And so those of you who are familiar with this kind of work in nuclear physics, it's very common. All experiments we do this way. We then gate it with this timing, because this timing peak, this peak will happen only if both the detectors fire, and the second detector comes at some time after the first. This width of this peak is called the timing resolution. So if you were to select a timing gate between this channel and this channel where this peak is, then this part would disappear. You would be left with this, and this part where the second detector has not fired at all, that would vanish away. So we will see that now in the next example. So this was macro 3. In macro 4 will be same as macro 3, except that we will gate. Now, so macro 4 will explain gating, how we make a gate. The channel number to gate is can be seen from here. If I were to explain the channel numbers, then you can see that from here I need to select a channel number which from around about 1000 to around 2050 or something like that, in order to gate it on this peak. So let's see that now. So I'm going to stop this one. I stopped it, and I quit root also. I'll start a new root session, and in that I'm going to load macro 4 instead of macro 3. So macro 4 will be the same as macro 3, only a gating condition will be applied. So let's see that macro 4. Here it is. So this is macro 4. Everything is same, the same loop, but here while filling after filling H4, there is a H5 also, which was not there. That finished with 4 spectra. Here there is a fifth spectrum. The fifth spectrum, I have given it T gated. I have given it in the title T gated here. And what it is going to do is that it will update this. See the definition of H5. Up to H4 it is a normal fill command, but this fill command is qualified by an if statement. So only if the timing signal is greater than 1000 and provided the timing signal is less than 2150, this was the gate which I was trying to tell you, then only you want to fill the histogram, otherwise not. So this is called as gating. You will see this in lamps, we call it as a one-dimensional gate. And here there is no such terminology like one-dimensional gate, and there is a two-dimensional gate that is called as a cut G. You have seen that while doing a telescope. But for one-dimensional gate, he doesn't give it a specific terminology, because he is doing it inside the C program like this. He doesn't have anything special in root. It's just you who's writing this C program, and you can always put conditions yourself. So he leaves this up to you. There is nothing special in root to do one-dimensional gating. You have to do it yourself, and it has to be done inside the event loop. And to do it, you just use normal C language constructs like this. So if you were to do this cobalt 60 experiment and you wanted to analyze it, and you wanted to put a gate on the timing peak, and then look at the gamma 1 versus gamma 2, then this is the program which you would have to write. Okay, this is the minimum program which you have to write in order to do any kind of. You must be familiar enough with C so that you can write such a program. If you do not know C++ and you do not know the commands of root, you cannot write this program and you are stuck. So this is a sort of minimum kind of processing work. The actual programs which you write will be very big. This is having 33 lines. You may have to write 300 lines or 500 lines to do the coding for your real data, but it would be basically like this. But the same data I will show you when you analyze in LAMMPS doesn't require any coding. So when we do this analysis of this exact same data in LAMMPS without writing any code, just by clicking in the program as required, we'll be able to complete the analysis. So this is the difference in the two programs. Root requires a lot of effort from your side. Anything you want to do in root, you have to write the program. You can't do, we saw with the GUI, I showed you, you cannot get the results which you want. This is the only way, and this way requires you to write programs in C++, and this is the way that you have to write, and you have to get trained in writing these C programs. This is the only way you can make progress in root. Now I have completed my 4 examples. I didn't run this, so I'll run it for you. So I need to execute it. Yeah. So this is the same thing, but here I have put a getting condition on the 5th spectrum. So it is otherwise similar to the previous macro. So like the previous macro, it has got all the other screens are the same, which you have seen earlier. This is the gamma 1 spectrum. Then this is your gamma 2 spectrum, which I mentioned that you have to zoom it in order to get it going properly. And this was your timing spectrum, which again you have to zoom it if you want to see. So this is as before. Then G1, G2 you have seen, but now comes another G1, G2, where you will notice that this bottom portion, so here I just zoom it, you see this one was without any timing gate. So apart from these 4 spots, there were also these 2 spots which are coming when the first detector has fired, but the second detector did not fire. So, but after putting the timing gate, you will notice that it has disappeared. Not only that, the random coincidences inside also are less, because you have put the timing gate, so only true coincidences will mostly be there, and some of them accidental coincidences are left here, but these have totally disappeared. So this completes my explanation for you of these how to write macros, how to make an event loop, and you can keep these programs with you for practicing, and with the help of these skeleton programs you can write such programs also of your own. Now before proceeding for the next step is that we will convert this macro into a complete program, and that will be the last and final thing. So but before doing that, I am going to show you how this exact same analysis can be done in LAMMPS also, and then we'll make a comparison of these spectra which are generated and convince you that they are the same. That will give you the clearest picture of how we are doing the data analysis work. So I should really have left all the canvases open, so I will run it again, so that I have all this. Yeah, I keep all these canvases available so that we'll be able to use them later on when we are running LAMMPS. Okay, so let's run now LAMMPS on the same data. So what we do is we start LAMMPS. LAMMPS is to be started from the same directory. We can do it, let's say I do it from another tab in the same directory. So I am in the same directory, and I am going to start LAMMPS by typing LAMMPS1. So I started LAMMPS. It's a new directory, so this default screen came. I am choosing higher resolution, and now LAMMPS has started. The first thing to do, so I am going to make the setup manually. You can just remember the steps for doing this setup. That setup file is not included, I think, properly in the folder which you have unzipped. So it is to be done like this. First you go to setup, and the only thing which you need in the setup, oh yes, before that I should explain that this program has been compiled with the root option. So I should perhaps explain that first before we go here, otherwise you will have a problem. Right. So let me explain that part first. So what you need to do is, some of you who have already compiled LAMMPS right in the beginning may need to download it again, because there was some change in the LAMMPS offline.tgz file. But those who downloaded it later on, for them they don't need to redo it, because the latest version is given in the website. So you have to go to your LAMMPS offline directory, This is my lamps offline directory, and here the correct file which you have to have unpacked is actually not this one. If you have this one, then please repeat it with this one. The first one was made available on 1st January, but that actually was a version which was meant for Ubuntu 21, whereas I think all of you must be using by now Ubuntu 20. And if you have some other Ubuntu version, not even Ubuntu 20, then you may find that this also doesn't work for you. I mean, whatever we did so far would work, but this link to root may not work for you if your version is different. So in that case, you can contact me and I will help you with another version which will work out for you. But assuming you have got Ubuntu 20, then what you do is you download this one from the website. This is what will come now from the website, and not this. And then you unpack it in the usual way, and then you go to the source directory for its compilation. And when you say make, then a choice comes. This choice asks you whether you want to build it with root capability or not. So if you if you have already installed root by now, which you would have, then at this stage you answer yes. And then in my case it's already built, so nothing happened, but maybe I should explain it by actual compilation. So I will just clean it first. So make clean will undo the make completely. So with this I have now removed the make. Now I will do make again. So building with root capability, yes, this is the important thing. Earlier on you might have done no. We do it yes, and then you will find that it compiles. But now it is possible to run it with for analysis of root data also. This is the difference. Without this, it cannot analyze root data. So that completes the job, and now it's ready. So I can it's ready to run. So I can go to my relevant directory and run from there. So I will come back here and open the terminal again. Now the command, so I'm running it now. It's I stopped so as to explain how to install lamps with root link. I come back now to this part which I was explaining. So what we are going to do now is we are going to run lamps. We are going to run lamps, and the command for that is lamps1, and we are going to make a setup. So the setup should be this one. Don't worry about anything here for the time being. We are going to have only 3 parameters. This is showing a lot more, but don't worry about it. Only thing important is this one. So change this to root, because our file is going to be a root file. So change this to root. This is the most important thing. You don't even need to switch this on or anything like that. Just only keep root here. Nothing else is important. Don't worry about the spectra and all. This will happen later on. Make sure that this is done, and then say that the setup has been completed. So I am going to say setup done. So it's over. These are still wrong. I mean, there are so many parameters. We have only 3. So this is going to happen now. Next important thing is go to setup and do a root setup. So apart from the setup, there is now a root setup also. And this is to be done provided your program has been linked with root. So edit the root setup. Now when you ask for editing the root setup, then he first makes this important thing that we are going to work with root now. So do not have lamp setup. In its place, go for root setup. So now we are going to work with root setup only. Then in order to get hold of the parameters, now this is the leaf name, it's all showing empty at present. We click this browse button here, browse root file, browse, we browse it, and then we must find the file. It is not in this directory. We go up and this is the file. So we click this, and you see here identified branches on his own. So we don't have to now name the branches or tell LAMMPS what are these branches. He knows about it because we have given the file and he has understood, and he has even given the tree name here. So he has identified the tree and he has caught hold of the branches. He has also understood what type they are. So they are unsigned short. He has understood and he knows the names also now. So basically with that we are now ready to analyze the root file, except one thing is that the spectra are to be defined. So we know that we want to define actually three one-dimensional spectra, gamma 1, gamma 2 and the timing. And that also LAMMPS will automatically do for you. You see already it is set without any effort on your part. He knows what you want from before. And similarly we want one 2D spectrum and he again knows what you want, 1 versus 2, 512 size. So already it is okay, nothing to be done. So LAMMPS that way is designed to operate for the kind of data that nuclear physics people will be using. It wouldn't work for other types of data that easily. So the root setup is also complete. So you say root setup done and you see the change in the parameter list. So you have gamma 1, gamma 2 and T now. These are the parameters. And now we can build the spectrum. So like before, you say analysis and start. And now when you try to add, it's not in this directory, you go up, it's a root file here. So it's not a CSV file but a root file, and you double click it, it gets added here like before, and in all respects it is same. Only thing is it's a root file. When you start the analysis, it's over, and then you click the spectra, it's seen here. So now we are going to compare what we got with root. So let's start with the G1 spectrum, and here it is. So I put them for you side by side, and as you can see they are the same. Now when it comes to G2, I mentioned that in root there is only the scaling problem, otherwise it's supposed to be the same. To get rid of the scaling problem, one can see here also the noise is there, but he doesn't scale it according to the noise. He changes the y-axis scale. So this one you need to change the y-axis maximum basically, or you can just cut the noise by zooming this axis. So I am doing it like this. So you see the same thing has come here also. Then the same trouble with the T is also that it is not in root. It has scaled according to the first channel, the last channel. See here also the last channel is showing a spike, but he doesn't scale with that, the y-axis. He is intelligent enough to know that this may be a problem, so he doesn't scale with that, but root doesn't know that. So in root you will have to zoom it, avoiding the last channel, and then you see that is the same spectrum that we have. And then this one here also we can zoom it like this, and here also you can zoom it, you see it's the same. Now if you want to get this one, then in LAMMPS we must do the gating. So that gating is to be done in the same way. You can do it, I'll show you once. So setup and then root setup, and then edit the root setup, and make a second two-dimensional spectrum. And in the second two-dimensional spectrum it will be the same 1 versus 2, but now number of 1D gates 1. And then in the definition of the 1D gate, choose the timing parameter, which is 3, parameter number 3. Low channel I think was 1000, something like this, and high channel was 2000 something, 2100 I am putting. So this completes it, and then we OK it, and root setup is done, and we analyze it again. And now we have this, so we compared all, but this one is new. So here you see, I can just move these away from you from here. We are going to compare this one with this one. So you see they are the same. I will zoom this part, you see. So this lower part has disappeared, as here also. Alright, so this was a comparison between LAMPS and root. It was trying to show you that these two programs which we have taught, they are supposed to be doing the same work for you, namely analysis of your nuclear physics data. The way to analyze them, we have, by the help of these examples, we have given you enough information, and you can see that in root, it's capable of doing anything, whatever you want. Only thing is the program has to be written. You have now seen how to write it as a macro, and the last, almost the last thing for today is how to convert those macros into full programs. That will be easy, so I'll just show you that. So I'm going to quit root here. Now what we did so far in root was we learned how to write these macros, and inside the macros we learned how to write what we want to do. If macros are enough, why do we need full programs? So actually macros are almost enough. There is only one problem with the macro, and that is that it is not as efficient. That means the running time would be slow. You see, what we are demonstrating here is very small data with very small number of parameters, and without any complications. When you start handling the real data, if you want, you can do it with the macro. It's possible, just like we have demonstrated. It is fine. But really speaking, you should go over to the program, because when you do it with the help of program, then it will run much faster. So how do you convert your macro into a program? It's very easy. You take the macro itself and just change it. One thing is that instead of calling it by dot capital C, you can call it by the name dot small cpp, and give it a new name. Instead of calling it just, I given it a new name because I don't want the same name here. And also to tell you, this dot capital C and this dot cpp, these are all conventions, and this is my own convention, nothing specific about root, that these conventions are forced on you. This first one could also have been called dot cpp, the macro, if I wanted to. There is no harm. Similarly, even the complete program could have been called with a dot with a capital C. There is no harm. But I prefer to have two different extensions so that I am able to distinguish the macro from the complete program. I know which one is which, so I don't get confused. And this is my internal way of doing the things. It's not necessary that you have to do that. If you want, you can change the convention, but you have to use either dot capital C or dot cpp. So this is my choice. Now if you look at this program 1.cpp, and if you side by side, if you look at the macro which was there, macro 1, right? So this was the macro 1. It had got only one line, and that was welcoming our students. If you want to convert it into a program, again you have that same exact thing. This much is same as that. Only thing, you must change the name. You must call it prog 1. There it was called as macro 1. So you change the name here. And important is that there has to be a main program. All complete programs must have a main. Macros don't have a main, so there is a main here. And this is about it. And other thing is that you must include all headers. In full programs, headers are required. So this is the header. I am putting RIO, and then you will have to put the namespace. Otherwise, you won't be able to do cout. So the namespace is standard std. And this is IOStream, but with root there is also there is also RIOStream, so you can use this. And one more thing is this. Now this is an optional thing which I have put. Many people don't know this trick, so you might see people writing the program without this one, which is also fine. Now this is an additional thing. which I have put, this one, this has got the benefit that now this complete program will run both as a complete program as well as a macro. So it can work as a macro also, because when macro is running, then this by help of this if, endif and endif, it will bypass this one. This part will not happen when you are running it as a macro, because of this one. So this part will go away and we get back whatever it was in root, except that we would have included the header, but if you don't need it in a macro, but if it is there, it doesn't cause any harm. So a complete program is written in this style, which I am demonstrating here, can be run as a macro as well as a complete program. So you may as well have only the complete program and you can forget about the macro, and you write your programs like this, and when you feel like it, you run it as a macro, and when you feel like it, you run it as a full program. So when your macro is running perfectly as a macro, then only you switch over to making it a full program, because the full program will run more efficiently. But on the other hand, it should not have any mistakes, and if there are mistakes, it would be hard for you to identify those mistakes. But when you run it as a macro, you will be able to more quickly find out the mistakes. So my recommendation is you write the thing like I have written it here, and first run it as a macro, and when it's successful, then you go for its complete programming. Now if it's a complete program, then you need to compile it, and with using G++ compiler, we are going to compile it. This is the command. In all my programs, I keep the compilation command also handy inside the program itself, so that here with my middle mouse button it gets just pasted, and then I just click it here, and now compilation is over. Now this is a complete program, it is not part of root, so you don't have to start by typing here root, you don't have to do that. You instead you make it dot slash and prog1. So this is just right running a complete program. It will run in this window itself. So in this case it will just print that welcome message, and so that got printed here, and then the command finished. There is no root at all. It's a complete program. Let's do that for the program 2, 3 and 4 also. So if I now were to show you program 2, then you will see it is the same as the macro 2. I just close these windows. So this is program 2, and macro 2 was demonstrated here. So this is macro 2, okay, and program 2 is looking the same. This part of it is exactly the same commands. Only extra is all the headers have been put. These are the headers, and now there is a main program. Now this main program, I had to explain, it is not exactly a dummy thing. There is now something called as a T application, the app, and then a call prog2 to this one, and then finally the app dot run. So never you will have to change these lines. So take this part as fixed for you. You will have to only change this name to match with this when you write, and this part you will never change. So it is a fixed thing. Basically what it does is that it makes the program get into a permanent loop, so that the program is stuck over here. And this is necessary, because otherwise if the program finishes, you won't be able to see these canvases. So these canvases will get created by all these commands, and the spectra will show up inside the canvas, and then the program, if this was not put, the app.run, then the program would finish and you would stop seeing the canvas. So the canvas would flash on the screen for an instant and then vanish. So we want the program to hang over here. So that's why after running prog2, that is this part, it's run, all the canvases are displayed, but this command, the app.run, makes the program get stuck on this line, so that it will not ever come out of this line. It will permanently hang at this position. So let's now see how it works, then you will understand. So we are going to compile it. This is the compilation command. So here goes. Now it has got compiled. How do you run it? It's the same way, dot slash program2. Now it will run. I need space to display the canvases, so I clear up all these things. Let me move this window down. the canvases will appear in this empty space. So I am running program 2, and see here it has started. But also notice what has happened in the command line window is that the prompt has disappeared. The program is hanging at this point. It is stuck. It is not released. My dollar sign has not come back. The program has got stuck at this point. That is what we want, because if it doesn't hang at this point, we cannot see these canvases. They would vanish. If I terminate this program, then these canvases will go away. So these are the canvases. Nothing much here. You have seen these canvases before. We got them working, and this is here. Now how do you come out? Suppose now you have finished. As I said, the program is hanging. How do you come out? So there are two ways. One of the ways is file and quit root. If I do that, then the program will come out. I demonstrate it. You can do it from this or that, any window, any of the canvases. You do quit root. See, now here it comes back to the command prompt. Second method is that after you get the canvases, second method is to, on this terminal window, you type Control C. You type Control C, it kills the program and it comes out. So both the methods are to be known to you. Let's try it for program 3 also now. Nothing much in it. So first we need to compile it. I'm not even showing you the program 3 listing because it is the same as the macro with only main program added. So here program 3 got compiled, and to execute it, / program 3. So you see here it ran. Same stuff. You need to zoom here and all those things. But it's the same thing. And the program is hanging here. And the windows are here. And when you have finished, you can quit root from here. Similarly, I think there is program 4. But anyway, by now you know what to do. So here goes. Program 4 got compiled, and I run it with / program 4. So program 4 is now running. Canvases are displayed, and when you have finished seeing them, okay, then you can kill. So for today, almost at the end. Now I would like to show you one or two things only. That is how you save. Yesterday I tried to show you because I think question was also asked that how do you save these pictures. So let's say this picture is to be saved. Then, as I mentioned, you click on file, and then you can, instead of clicking on save as, you can as well click on save, and then you will see that he has got the options. So C4 is the name, canvas 4, and then you can have PNG, JPG, GIF, whatever you want as the different options here. And in fact, there's also C4.C. This will create a macro which will, when you play back that macro, it will reproduce this canvas. So these are all the options. So let's save it as a picture file. Let's say JPG. So I saved it as JPG. So then the command, it reflects here that he has done it. If we have a look here, you will find that the picture has come here. See, so he is able to save this picture. So this is how you can save pictures. Now let's see how we can, I was trying to delete it, yeah. Let us see how we can save the histograms. There's also very important thing is that you see now when you do the actual data analysis, these histograms are not going to come on your screen in a fraction of a second. It's going to take several hours, in a real data analysis time. So the histogram will take a long time, maybe not always hours, maybe minutes, but sometimes even hours before the histogram is ready. After the histogram is completed, then you would like it to be saved, so that in case there is something, you make a mistake, then the histogram will go away and you have to start again. That is something which you want to avoid. So generally what we do, we try to save the histograms. So this is important, and this will be my last topic for today, is how do you save the histogram. So to save a histogram, you can't actually do it now from this macro. It is not possible. You should anticipate this requirement and put it inside the macro itself, your command for saving the histogram. So let me come out of this running program either by Control C or by quit root, and let's modify one of our macros and put inside it some commands which will help us to save the histogram. So let's see how that can be done. So let me modify, let us say, macro 3. So I pick up macro 3, open it with editor, and then I go to the last line. So at this point, the macro is actually built up 4 canvases, and he has drawn all the histograms. But once the macro finishes, then all the histograms are lost permanently. So if this program has really been running for a long time and it is better to save the histograms, then what do you do? So the command is that first you must open a file. The name of the file is up to you. So we are going to open a file. I am going to say TF. Now TF I am reusing. Actually TF is already here at this point. So first I should, if I want to do it correctly, I should actually close this TF. So let me close the previous one. Okay, so we have finished with our work on the Cobalt 60 root file. So we close this. So now this file is closed. Now this variable TF itself I can reuse, or I can have a new variable. It's up to me. I am going to reuse this TF variable because we have finished with this TF. So let's open another file in which we are going to save the histogram. So I use the same variable TF, and I will open a file by putting TF is equal to and then a new. Now histograms are generally saved inside root files. So root files is not only a container for your list mode data, it's also a container for your histograms. You can actually even put these histograms back into your original root file if you want. But then generally we don't like to spoil the original data. So this is the original data which you might have got from the experiment. I don't want to write histograms into that. It's better to leave this without any changes permanently, whatever we got during the experiment. So let's make a new file. So what we do is we say TF is equal to new, and then we new T file. Okay, and the command will be similar to this one. So it's a new T file and it's also a root file, and give it any name where you want to store. So let me call it as histograms histos.root, for example. It must have the name root. The extension name should be root. So inside this root file I am going to save the histograms, and then I need to write. So this command by default can only read. You cannot write into this file. It is locked for reading only. So I need to give an option here. So there are two options which you can use. One of them is new. So if you give with new, then it will create a new file with this name, and which is good. But one of the problems is that once you have done it, second time you make the run. So suppose you make this and then you find you want to make some changes, and after the file histos.root appears, second time onwards he will not be able to write because he will complain that this file is already there. So what I usually prefer is recreate. Recreate means overwrite. So it will, if suppose this file is not there, then it will make it for the first time. And if the file is already there, then it will delete that file and open it fresh. So this command is more useful in this case. Now we can write any histogram inside it. Suppose let's say H4. We have 4 histograms. We can write all of them one by one, or let me for this demonstration write only one of them. So H4 I am going to write. H4 and then just write. This is the only command. And where will it write? In which file? It will write it in this file only because this is the only TF which is opened. So he will write it in this. and after we have finished we should close it. So TF should be closed. So this is my modified version of macro 3, and when I run it, it will be like before, but the extra thing is that a new root file will be created and it will have this histogram inside it. I'm going to demonstrate it. So I now save this file. I saved it, and then I'm going to now run it, and when I run it, a new file will appear here in my directory. So this macro is macro 3. So I can, this is a macro now, not a complete program. I can do it in the complete program also. So root and then macro 3. All right. Yeah. So this new file has got created here, and I will just show that, and then I'm about to stop in any case. So let me see this. Yeah. So if I do now new T browser, then I try to look for my file. See, here it is. So I click it, and then you see it has got H4, and if I double click it, you see it gets displayed here. So that's it. I think I have demonstrated what I wanted to show you.